Okay.
Okay, welcome everyone to HAO Colloquium today by Dr. Emily Mason. It is my great pleasure to introduce Emily. Dr. Emily Mason earned her PhD from Catholic University of America in 2020. Her thesis work centered on extreme ultraviolet observations of coronal rain in low coronal null point topologies. She won a NASA postdoctoral fellowship at the Goddard Space Flight Center, where she worked on Hinode coronal hole observations. She has studied the characteristics and implications of coronal dynamics in a range of topologies, from coronal holes to solar flares. Dr. Mason joined the research team at Predictive Science in 2022 and has been focusing recently on time dependence and the quantification of topological change in magnetohydrodynamic simulations. So today, Emily will be speaking on flare onset secrets from variable emission in cool plasma. So to Emily now.
Thanks. And thanks for inviting me. So this is my talk. I've been working with my student Karen Yazuski, who's at the Air Force Institute of Technology. Vadim Uritsky and Seth Garland have been helping out with this project. So I am happy to talk about it today. I'm going to do things kind of back to front. I'm going to start with a summary of the main points, and then we'll get into how we got there. So basically, for the study that I'm going to be talking about most of the time, we investigated off-limb emission prior to about 50 major flares, C5 and above in the GOES classification scheme, with SDO AIA for 6 hours before flare onset. We found that there were erratic, short time scale, non-periodic fluctuations in the emission that occurred in active region coronal loops hours before flare onset that were basically entirely absent in similar active regions that were not about to flare. As part of those fluctuations, we found that particularly in the 131 channel, there were these spikes that were tied to very short loops that became very hot very rapidly, that were more closely tied to confined flares than to eruptive ones. So that was an interesting finding. And the nature of the fluctuations basically hint that these are local changes in the coronal portion of the loops themselves, as opposed to being a change that's being conducted upwards into the loop from the photosphere, the transition region. And the point that I'm going to keep hammering home at, if you remember nothing else from this talk, it's that lateral thinking is important. We almost missed the forest for the trees on this one. So I'm using it as kind of a warning story for everybody to break out of how we usually think. So we'll start with some background for anybody that's not a solar flare person. Solar flares, at the base level, they convert magnetic energy into other kinds of energy, mostly electromagnetic radiation, thermal, and kinetic energy. This is not an exhaustive list, but a few of the basic things that we do know and understand about flares are that they are a rapid release of stresses that can have built up anywhere from hours to days to weeks at a time. There are a lot of factors that go into building up those stresses, and they work on very different timescales. But the release, the actual flare itself, tends to be seen as a very rapid process, which I'm actually going to challenge a bit of in this talk. The more complex your magnetic field in your active region that hosts the flare, the greater chance you have that it is going to flare. And if a region has already flared, if it has a history of producing solar flares, it's probably going to continue to produce solar flares. But the process produces both hot and cool plasma, and both of those are important. And we'll actually be focusing mostly on the cool plasma in this study, with the exception of the 131 spikes. We'll get to those. So what do we not know about flares? There are still a few really potent open questions. One of the biggest is what triggers flare onset. We know that the system gets to this stressed point, but it can also sit at that stressed point for a chunk of time before the flare actually kicks off. So what starts that? Where do you get from the stressed point to the point of starting to flare? We have not figured that out, largely because each flare is a little bit different. How energy is distributed throughout the active region during a flare is still a very active area of research. And I would argue that we actually don't have a great idea of when a flare actually begins. And that, as this study shows, there are changes that are occurring well before the impulsive phase starts, which we usually think of as being the spike in the X-ray flux is what we start marking flares from. But there are changes that happen well in advance of that. So I like to push back against the idea of when a flare starts. That time span is a lot more mutable than we usually talk about. But if you're not familiar with flare dynamics at all, let's take a step back and talk about the standard model. So with the standard model in a solar flare, you start with a neutral line. One area of, say, positive polarity, the other area is negative, butting up against each other, like these two yellow patches here with coronal loops connecting them. A lot of recent work agrees that one of the fastest ways to build up the necessary stresses to kick off a solar flare is shearing. Basically, these two yellow patches moving in opposite directions from each other. And once you get that, it stretches and stresses those magnetic field lines that are connecting them. And the system wants to find its way back to a less stressed state, kind of a ground state. So it needs to get rid of that stored energy. And it does that by magnetic reconnection. So these field lines, as they stretch and get kind of bunched up next to each other, you start getting reconnection. And that reconnection forms a magnetic flux rope here and the beginning of an arcade down here. But that flux rope can actually sit there for a while. This is part of that trigger problem that I talked about. You don't immediately get a solar flare impulsive phase kicking off. But once you do get that transition, you go from this phase over here to this phase, step 3, where the flux rope destabilizes, and then you get a flare arcade down here. This is this red arch. Magnetic reconnection is happening here. And if you have an eruptive flare, you get a coronal mass ejection. This flux rope shoots out of the corona into the solar wind. Maybe it hits Earth, maybe it doesn't. Or if you have a more complicated scenario, either there's too much overlying flux that won't let the flux rope rise out, or it reconnects with a bunch of neighboring magnetic field lines or structures and it chews through that flux rope, then you just have a solar flare with no CME. So already we have a lot of ifs. And if you pair that with the trigger problem, you can already see part of why flares are so hard to predict. Pinpointing when and where a flare is going to happen is extraordinarily difficult. Flare prediction, we have dozens of methods already, but it's really still kind of in its infancy. We're still at the nowcasting phase. We're at the point of going, ooh, the X-ray fluxes are starting to go up. We have a flare starting, rather than going, we think there's going to be a flare here in 3 hours or tomorrow or something. Because no single consistent measure tells us how and when the magnetic field will catastrophically destabilize. The how part isn't really the sticking point. It's really the when that is so hard to pinpoint. And like I said, this is because we really don't understand the trigger point very well. So what kind of signatures have we looked for already? We've looked for observational precursors. Historically, a lot of the methods have focused on looking at the magnetic field, the photospheric magnetic field readings. More recently, more of the methods have started using extreme ultraviolet, EUV emission, and a lot of those are starting to incorporate machine learning methods within that. A lot of those tend to be built on the, if an active region has already flared, it will keep flaring idea. And in controlled studies, like the first studies that each of these like methods put out, they have really promising detection rates. And then when it's turned into more of an operational thing, those percentages tend to go down. And this is not a dig at any method. Ours is probably going to do the exact same thing. This is just showing that prediction is really, really hard. So our project is based entirely on EUV observations, although my student has been making some excellent progress working with magnetic field data. She has a paper that's under review right now. Hopefully that'll be out soon. But this part of the project is on the EUV. So let's talk about some of the plasma during a flare, especially cold plasma. So on the sun, you tend to get kind of two types of cool plasma forming in the corona. So catastrophic cooling under a couple of really specific conditions can produce knots of cool plasma from lots of hot plasma. So this is not plasma that is being thrown up into the corona from like the chromosphere transition region. This is plasma that was at a coronal temperature and cools down to photospheric temperatures. And the two ways that you get that, you can have post-flare rain, which you can see in this movie over here on the left. Flare starts, and then you get this whole bright arcade here, and you can see it's very coherent in some ways. This is very clearly an arcade. You can see all of these loops are pretty well lined up. Each loop rains once, basically, and then you see that arcade kind of growing. That's because it is successive loops at higher and higher heights that are cooling down and draining. So, but it's very coherent both spatially and in time. You get the lowest loops, then the next highest loops, the next highest loops. So that's your post-flare arcade rain. The other type of rain is kind of more erratic, and that is often called quiescent or thermal non-equilibrium driven rain. So this is the rain that you can see like here and here, where it's all different loops at different times. If you watched it for long enough, you would see the same loops rain again and again. This is a cyclic pattern that occurs as with steady heating, actually. So your post-flare rain is more from impulsive heating. Your quiescent rain is from steady heating. And like I said, the post-flare arcade rain is a one-time process per loop, whereas thermal non-equilibrium can recur over and over every couple of hours for days. But both types have actually been key to uncovering flare dynamics, and that's what we're going to be talking about in the studies that we did. So this actually started a couple of years ago. We did an initial paper where we were studying flare arcade rain. Because everybody knows it exists, but nobody had ever actually sat down and quantified how common it was in different types of solar flares. So we just did a basic benchmarking statistical study to show how common flare rain was. But we found a few additional interesting things. So we looked at 250 flares from GOES C1 up to X. 7 or 8, I think, was the highest flare class that we had. We looked at on disk mostly flares, and we found that the post-flare arcade rain occurred in most M-class flares, basically nearly all X-class flares, and some C-class flares. So it was actually fairly prevalent from C5 up, but C4.9 down, the incidence dropped by a factor of like 2 to 3. So it's kind of hinting that there's actually a kind of energy minimum, that if you're not dumping enough energy into post-flare loops, they do not get hot and dense enough to create post-flare rain. The flare rain did not correlate with eruptivity at all. Whether or not there was a CME had no statistical tie to whether there was rain or not, which honestly wasn't that surprising, because once you create the flare arcade with the reconnection, the flux rope and the arcade have pretty much nothing to do with each other. But the flare frequency, the percentage of M-class flares that had rain, actually tracked with the sunspot number quite well through solar cycle 24. So that might be an interesting thing to look at for future solar cycles of if your percentage of flares, M-class flares with rain is shooting up, you might be looking at a fairly strong cycle. But one of the things that we did notice was that there was a distinct shift because some of the post-flare rain would go on and on and on. And we were like, okay, 2 days after the flare, this is not still post-flare rain. And you could tell that the arcade loops would grow up to a certain height and then they would just sit there, but they would keep raining. And after a bit, we realized this was a transition. This was actually an energy shift from the post-flare arcade rain happening because of the flare dynamics and heating to the quiescent rain where you were starting to set up that steady heating regime and you were getting TNE in those loops because now they're just normal coronal loops. So your arcade can just turn into normal coronal loops afterwards and continue the same kind of quiescent rain patterns that you would get in a normal active region. And it seems to be kind of part of how the active region sort of resets after a flare, or a way that you can tell that it's reset. But one thing that we didn't publish in the paper was a tendency that we noticed that some of the quiescent, the TNE rain that we were looking at seemed to vanish hours before another flare started. So we kind of noticed that. We chatted about it for a while. We were like, we should look at this because it looked like there was some kind of heating that was happening. Maybe that was enough before the flare that we thought it might be a useful precursor. So we started out investigating the coronal loops in off-limb active regions so that we had a nice clear view of the loops and we could isolate it, because if you've ever looked at 304 on disk, you know you're basically looking at the chromosphere. You can't see if there's something in the corona. You can't tell what it is or where it is. So we looked at off-limb active regions and we looked at a handful of cases, and just by visual inspection, like less than half the, just under half the time, the rain decreased ahead of flare onset, which is not a really strong correlation. And this table here shows those initial emission trends that we noticed. And it was split pretty much 50-50 for a lot of them between whether the 304 emission actually went up or if it went down. There was a non-negligible percent of the time that there was just chaos. That sometimes you had more, sometimes you had less. There was no pattern. And sometimes it just kind of seemed to be steady. So by theory, like coronal loop theory, there's a few ways that the emission might change. So if you have heating being added to the loops, you would expect the hot channels emission to increase and the cool channels emission to decrease, unless you're looking at TNE where the heating's only being dumped at the foot points, and then you might be looking at something that looks more like a cooling pattern where the hot channel emission decreases and the cool channel emission increases. Other possibilities were that the loops were just growing, which is known to happen before a flare, in which case you would expect all of the emission to decrease because your EUV emission is optically thin, so it goes as your density squared. So if your loop gets bigger, your density goes down. Or maybe even chromospheric evaporation, where you're just pumping a bunch of plasma density into the loop rapidly, in which case all of the emission might increase, although that shouldn't last very long. So we started extending the study. We started looking at some more channels, and the problem was that we saw all of these patterns. Much of the time, it was just chaos, where the channels seemed to be moving with no pattern, either with respect to each other or as a universal increase or decrease there. So it was a mess. And I'm going through all this detail because at this point, we nearly threw the whole project out as a null result. And then thinking about it, I was like, there's something here that we're missing. And much like this picture, a lot of things depend on your perspective. And I thought maybe we'd been looking for the wrong thing all along, and it doesn't actually matter whether the emission's increasing or decreasing. We're seeing all this chaos, all these fluctuations. Maybe the variability is the thing that matters. So we decided to dig into the variability, and that's what became the rest of the study. Now that we knew what we were looking for, we honed in, we used 131, 171, 193, and 304 as our 4 channels because that gave us a very nice spread from like 50,000 Kelvin to 10 megakelvin to work on with AIA. And we took, in the end, we had about 52 flares from the from C5 up, basically. Although we only ended up having 4 X-class flares because of how stringent our observing criteria were for it. So when I show the graphs for X classes near the end, I'll remind you to take those with a grain of salt because it was an N equals 4 pool. So we took 52 flares and we took 30 non-flaring active regions as a control group. We made sure that they were of similar magnetic complexity and that they also had produced flares, just not when we were looking at them, just to make sure that we weren't accidentally including regions that were fundamentally different from a flaring active region. We only used limb flares, so that was something that was either the 850 arc seconds or further towards the limb. And to ensure isolation so that we knew that we were looking at the loops we wanted to be looking at and nothing else, we had to make sure that there was minimal contamination from other active regions along the same latitude, so we weren't getting line of sight contamination at the limb. And we made sure that there were no major flares for 6 hours prior to flare onset, because that was our time window. So the approach was, as you can see here, here are the 4 channels that we used with little polygons drawn on. These were our regions of interest. We manually selected the regions of interest for all of these flares. We made sure that we did not clip the solar disk with any of these, but we got very close to the edge, which ended up being really good because the 131 spikes were tied to very short loops that were very close to the limb. And this was an incredibly tedious process that as we go forward will definitely need to be automated. But we drew all of these. We actually drew 2 separate sets completely independently and then cross-checked each other's coordinates with each other and to make sure that we were picking good regions. And so we took, like I said, a 6-hour time window pre-flare, and we took data at a 3-minute cadence for this. And then we just took all of the emission within those regions of interest, those polygons we had selected, and integrated that emission and plotted the normalized emission for each channel. And here are a few examples here for 3 of the cases. And you can see there is a fair amount of variability. Some of them are more coherent than others. Here's an example of one of the 131 spikes. Sometimes there's chaos. So this is just wildly varying, but they're fairly coherent. Here, these are varying more slowly and there's more of an overall trend, but the trends between the channels don't necessarily match. So there's a lot of variability here. For the control cases, we did the same thing, 6-hour window, 3-minute cadence, except we took a 12-hour period where there were no major flares, and we selected the 6 hours in the middle. So that was how we did the control cases. But the rest of it was the same. It had to be a limb region. We selected the region of interest, integrated over it, plotted the normalization. And if I just flip back and forth between these a couple of times, you can see visually there is quite the difference between the flaring cases and the non-flaring cases. So let's start out by focusing on these 131 spikes. Talk about those for a minute. So this is actually showing one of the cases that had multiple 131 spikes. 131 I actually picked because it detects 2 different plasma populations. You've got a cool contribution at around 100,000 Kelvin, which is most of the time that's your kind of fuzzy emission over here. And then you get the 10 megakelvin emission, which is all of these areas that are flickering and getting really bright. About a third of the cases out of the 52 had spikes in the 131 that did not appear in the other channels. Some of these were just really weak flares. Remember, we selected that there couldn't be any C5 or greater during that 6-hour window. But for instance, right here, that flicker that happened was, I believe, like a C2 flare. So some of them were weak flares, but a lot of them, like this area right here, was not tied to any GOES X-ray emission. It's just something happening in those loops that is making them very, very hot, but does not qualify as a traditional flare. The interesting thing about these compact loop brightenings was that they were 3 times more likely to occur before a confined flare where there was no CME as they were before an eruptive flare where there was a CME. And that's interesting because this is one of the figures from our first paper that showed that about less than a third of M-class flares are non-eruptive, and less than 20% of the X-class flares that we looked at were non-eruptive. So for it to be 3 times more likely to occur for a confined flare is a significant correlation. So there is something happening, or more likely failing to happen, in these cases that that are resulting in these compact loop brightenings. So a lot of energy getting dumped into these loops that is not eventually getting turned into the ejection of a flux rope. So that was the 131 spikes. Now to look at the differences in the cases between the flaring and the non-flaring, we took a few different approaches to compare the variability. We looked at the standard deviations of the different cases. We did structure function analysis and detrended fluctuation analysis. So I'll take each one of those one at a time. So first, looking at the standard deviation comparisons, we pooled these graphs along here, show hours before the flare. Now this is, the axis here is kind of flipped so that the start time of the flare is at the right edge, and this is increasing number of hours before the flare. We pooled the cases both by GOES class, C class on the left, M class in the middle, X class on the right, and by AIA channel. So each line here is representative of a different channel that we looked at. And then we pooled the flaring and the non-flaring cases for each of those and took the ratio of their standard deviations. And this was just a way to quickly measure the actual variability and compare the variability of the flaring cases to the variability of the non-flaring cases. And the hours are cumulative. So this is not at 1 hour before the flare, at 2 hours before the flare. This is all of the data from the whole hour before the flare. This is the first and second hour before the flare, etc. So it's more data as you go further to the left in each plot. And you can see I'd like to point out, first of all, that 1, which would be saying that the standard deviations were the same between the flaring and non-flaring cases, is at the bottom here, and none of the values touch it. So right off the bat, for every wavelength, every case, the flaring cases are more variable than the non-flaring cases for each wavelength. For the C class, you get a peak with the 131 and the 304, which are consistently the two that have the highest ratios. You get the peak in the hour before the flare. For the M class, the 131, the peak in the standard deviation variability is actually 2 hours before the flare. And then asterisk, remember, we only had 4X class flares, so take this with a grain of salt. But the peak for the X classes was 3 hours before the flare. So it looks like the variability increases more time ahead of the flare if the flare is bigger. so that there's a positive correlation between when the how early the variability starts and how strong the flare is going to be. And the 131 and 304 were consistently the ones with the highest peak values of the 4 channels that we studied. This graph over here shows that 60 to 80% of the flare cases standard deviations exceeded the controls. So this is the actual percentage of the individual flares for each class and each class and each wavelength that exceeded the control cases. So that's quite a high number. Then we moved on to the structure function analysis. And structure function is an averaging of a time series over bins of different sizes. We chose exponential bin widths here because that's better for handling sparse tails in data distributions. So, so the x-axis here, sorry, this is super tiny, but this is time scales increasing to the right log scale for all of these. This row is the C class, this row is the M class, this row is the X class. You can see how small our pool of the X classes were by how gigantic the confidence intervals are for the X class. So pretty much just ignore this one. But if you look at the C and the M class, the slopes are consistently lower for the flaring cases compared to the non-flaring cases, which points to rapid fluctuations as being the main variability driver, because as you go to longer time scales, it kind of flattens out. So definitely the short time scales on the scales of a few minutes to 10 minutes maybe are the fluctuation time scales that matter the most for the variability. And then the detrended fluctuation analysis was the last method that we used here, which is an averaging of the difference between a time series that's broken up into different linear bins and a fit to that time series within a given bin. So it's kind of like averaging residuals, sort of. And this method is used, the equation for it's over here, if you care. And the method is used basically to weed out any kind of external influence on pattern finding and to focus on something that is internal to the system. And the value of these slopes, which are pretty much for the 131 and the 304, again, they're the best. They have the greatest separation between the flaring and non-flaring cases. The slopes of these are all about 1. And for detrended fluctuation analysis, that corresponds to 1 over F noise or flicker noise. So it's just more evidence that this is pushing towards small, localized, short-term fluctuations that are driving these variability changes. So I say wrapping up, I have more slides. The main findings of this paper, which just came out in December, I think, in AppJ letters, are that, like I said, the loops above flaring active regions were consistently more variable than non-flaring loop cases, 60 to 80% of the time in all 4 wavelengths, with the 131 and the 304 being the best channels to observe that in. So again, because the 131, it has the hot spikes, but the rest of the time that flickering, that emission is the cooler plasma, and 304 of course is cooler plasma. You're seeing that there's variability in the cooler plasma that is hinting at changes that are building up towards a flare coming. That variability generally peaks 1 to 2 hours before a flare. It may be that you get more warning the bigger the flare is, but we need to test more X-class flares before we can say that definitively. And that variability is dominated by rapid changes. These are things with timescales of a few minutes, which is hinting at really localized things happening in the loops as well as the kind of flickering nature of them is hinting that it's actually in the coronal part of the loop, not a more uniform change that's being propagated upwards from changes lower down in the corona or the transition region anywhere else. And the spikes in the 131 were much more tied to confined flares where no CME is released than for eruptive events, which is potentially very useful. It's at least very interesting. Our next steps, there are so many of them. We have two main directions that we can go in basically for this, and Kara and I have kind of divided up between the two of us. She's taking most of the science pursuit for her PhD thesis. I'll be helping her with that, obviously, but she wants to spearhead this. We're going to be isolating the fluctuations, both spatially and temporally, to figure out what the actual characteristic sizes of the fluctuations are. We've looked at it mostly just in the time dimension, figuring out, you know, how long these fluctuations are, but we haven't spent as much time, any time really looking at how isolated they are spatially, or if we can pinpoint where they're coming from in the loops at any given time. We need to figure out what is causing the variability. One of the leading suspects, my favorite horse in this race, is coronal currents, that there's actually like currents driving component reconnection among the loops ahead of time, that's kind of driving up that stress, or possibly trying to relieve that stress before it hits the point of a flare. But we don't know, we won't know until we do more work on it. And definitely studying the 131 spikes in greater detail, seeing if we can trace what is happening to those and why those compact brightenings are happening, and what the cause is that that's occurring instead of an eruptive flare. From the operational perspective, since this was the fluctuations are so obvious, and the method itself of just kind of drawing boxes around bright areas and counting up the emission in it is fairly lightweight and easy to automate. We are looking at potentially testing this in an operational context. But way before we get there, we have to test this on much less isolated and perfect cases. We only did 52 initially because it was so hard to pull out cases that had sufficiently low line of sight contamination and didn't have a bunch of flares before it. So we're going to have to take all those things away one by one and see if we can still pull out the signal. We need to test cases with more line of sight contamination, test it with on-disk flares, see if we can still pull out the signal, things like that. And then move from this study, which was basically predictions of flares that already happened, to converting those variability measures into predictive measures, figuring out thresholds and everything based on this to determine how to figure out the timing and the flare class predictions. Because sometimes the variability levels at different time bins are the same for different times and different flares. So you could look at a variability and say, well, that could be a C-class flare in 2 hours, or that could be an M-class flare in 3 hours. And that matters if you're looking at doing it operationally. So I'll be taking on that behemoth. So my final takeaways on this, we have a lot more work to do. It was a very interesting and promising initial study, but there's a lot more work that we have to do to get this to either be able to explain what's happening or to use it. But also, I think it's time to revisit the idea that a sudden increase in X-ray flux is the beginning of a flare, because there are a lot of things that start happening well before that don't seem to be part of the building up of the stresses, like the creation of the conditions to create a flare, but seem to actually be a process that is leading to the flare itself later. So what we think of as flare onset is just the impulsive phase. There are not impulsive phases before that should be thought of as part of the whole flare event itself, because we're kind of we're essentially looking at flares. We're all the blind men and the elephant. We're all looking at different parts of it going, okay, this is what we know, this is what we know. And I think we need to kind of broaden out how we look at flares to get a broader view on it, which leads into my last point, the one I said I was going to keep hammering at, which is the thinking flexibly. We spend all of our careers becoming extremely knowledgeable about extremely specific things, and that is something to be proud of, and that is we are very, very good at it. As we do that and hammer away at that day after day after day, we are so used to looking at the same couple of problems the same few ways, we start losing the forest for the trees. And every great discovery in science has been from somebody kind of taking a step back and taking a broader view of things and going, oh wait, we might be able to use that for that. And like I said, we nearly stopped this entire project a year ago because we were like, well, no result, this wasn't doing what we thought. Because we were looking for one specific signal, or they're looking for an increase or a decrease. And that's been the story of a lot of our work. But in the end, in this case, it looked like the actual signal was not an increase or a decrease. It was just the fact that it was changing. And that let us kind of take a step back and go, oh, wait, maybe there's a more important signal here. Maybe we're missing something. And that's honestly, it's kind of scary because where else are we missing the forest for the trees? So if you remember nothing else, if you don't remember anything about our statistics or our variability or anything, just look at one of your projects and ask a sideways question about it. Just like what have you not thought about? If I can encourage anybody to do that, then I'll consider all of this work worthwhile. So yeah, with that, thank you. I'll take questions.
Thank you. Questions from the hall and from online. Sarah, yeah.
A really interesting talk. So you mentioned a little bit about what might be causing this, and you mentioned currents and component reconnection. And have you looked at have you seen things like this in simulations, for example?
So I cannot think of any flare simulations with this kind of flickering. There is, I mean, obviously I'm from predictive science, so most of my experiences with mass. If you look at some of the stuff like our eclipse simulation for the 2024 eclipse, if you look at the forward modeled like STO emission of just things rotating on and off the limb, you do see a lot of flickering that looks similar, although I think that has more to do with the way we integrate the line of sight for that. But it is a similar kind of dynamic. So I know Cooper often chalks that up to TNE and those kinds of structures. It may have to do with the heating, but definitely for flare simulations, I haven't seen this kind of flickering before.
Other questions? Anyone from online? Yuhang.
Yeah, thanks for the interesting result. So you are saying that the occurrence variability is big for, flare regions, but comparing to eruptive flare versus confined flares, the variability is higher for the confined flares. Is that right?
No, just the 131 spikes are more commonly related to that, but the variability overall, we didn't see a difference between eruptive and non-eruptive.
Okay. Okay. So this cannot be used as a way of determining, what kind of flare it's going to be. It's they're pretty much the same for the eruptive.
Yeah, for the variability. Yeah, the 131 spikes do seem to hint that the coming flare is going to be confined, but that's the overall variability is the same regardless.
Thank you.
Any other question?
I can make a totally wild, off-kilter speculation reflection, which kind of, I guess you're kind of asking for, right?
Yeah, I love that. What do you got?
It's just an impression, and I'm probably being very naive too, but I was in Iceland last year, and when you were talking about this, and we saw geysers, and the geyser, when you sit there and you stand there, and you wait for it, and you wait for it, and you wait for it, and there's a point when you know it's going to blow because it's going blah, 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 and then it goes. And I'm curious what's going on there, for causing that, and if there's any chance this could be related to the kind of thing you're looking at.
That could be. So when I was teaching myself about the detrended fluctuation analysis, because this was not something I knew about going, and this was something the team advised us to do. So I was reading up on it, and it did say that the 1/f noise that the slopes on the DFA analysis corresponded to are found throughout geophysics. So like there are many systems that show that same pattern when you analyze their time series with it. So that's actually not off the wall at all. It's entirely possible that the geyser, if you did the eruptions or vibrations before an eruption or something for the geysers, it would also show the same DFA slope as what I just showed.
Yeah, and then I guess the follow-up on that is, do people, I don't know if people care about predicting geysers exactly, but have people studied that as a means of prediction? Who knows? I'm going to Google it. We'll see.
Let us know.
I was thinking that you showed a few flare parameters, and similarly, some other people have focused on some other parameters, and then many people have looked at several parameters. And if you combine all those parameters and study all of them pre-flare, then is it possible, or is it too vast, or is there a way that by studying the vast parameters, flare parameters, one can predict little bit several hours before, instead of just only a few hours before, that something is expected? Or maybe, I don't know.
Do you mean kind of like doing like an ensemble forecast of like
Right.
a bunch of different?
Yeah. Like you presented here a few parameters, and then some other people worked on some other parameters, like polarity inversion lines, then number of null points, or all those things. Then if you combine all those parameters, then is it possible? First of all, is it possible? And if it's possible, then can it do a good job that you can increase your forecast time?
There are a few, well, I know Katie Lecca has put out multiple papers over the years, kind of evaluating and comparing different flare forecasting methods to each other. There was also another paper that came out more recently. I am blanking on who led it, but where they took basically the models from the, I think it was from the CCMC flare scoreboard, and put together kind of an ensemble forecast using the data from all of those for as long as they've been on the scoreboard, and kind of put together like a weighted average of them based on their accuracy. So so there are people who have been doing that. We're trying to work on pairing up. So like I said, Kara's been working on doing some extrapolations of the magnetic fields for on-disk flares, because we only know that this works kind of for off-limb. We have not moved it on-limb, like on disk yet, because that's going to vastly complicate analysis. But obviously, if it's on disk, you have magnetic field data, which we don't have on the limb. So she studied a bunch of parameters like the currents and twist and stuff like that, doing extrapolations for her master's thesis, and found that some of those parameters actually, she applied the same thought process that we had here of like, oh, maybe just fluctuations matter, and found that several of the extrapolated quantities for the magnetic fields also have correlations in that they become more variable in the hours before a flare. So ultimately, this method will be a combination of the two, where you have like the EUV portion and the magnetic field portion, with looking at the fluctuations to be able to predict the flares. So we are moving towards that. It's just slow going to make sure it works.
Yeah, thank you.
Mm.
You
I have another follow-up question. So you've done with this just for active regions, right? You have not looked at those quiescent prominences filaments, because those are some of them are ready to go as well, and they might. Is it because the field is weak, so you can't detect these precursor variability, or you just haven't looked? I mean, is there a field strength dependence because of this thing? Because it could be the active region is very complex, but it's a weak active region. So you sort of, they are doing, as you say, these component reconnections about it. It's just going to be a weaker signal. So I'm just saying, I'm just saying that if you have included like these large, more weaker field, but it's still precursors ready to go, would you see similar signatures?
Yeah, we have not looked, but that is a great idea. I would expect to see the same kind of precursors, but probably on longer time scales.
Yeah.
Like, because I mean, you know that
probably look at the
sit there for days. Yeah.
Which wavelength? Anyway, just a thought. So.
Yeah. No, that would be very interesting to look at.
Can I ask, you had a plot where you compared them for the different size flares, and you said that the 131 spikes, tended to happen even with a small number, but for the X class. But I don't think there was a huge difference in the behavior of the flare size for the other variability levels. Is that right?
What do you mean? Here, let me pull.
Yeah, pull up that plot. There was a picture with the one which showed the X, that one. Yeah, so if I look at the other quantities, the non-131, the variability, as you pointed out, is always well above 1. But I don't automatically see any kind of qualitative difference in the other ones. Is that right? So that there's not some, like...
Oh, you mean like the other lines?
Yeah, exactly. They're all more variable, but they're kind of similarly more variable independent of this class, which kind of pertains to what Yuhong was asking about the energy. That's why I was wondering.
Yeah. Yeah, I think it's because you have so much more diffuse emission for like 171 and 193 that it just really, I think the main thing is that the cool plasma is what's really changing. Like the hotter plasma does not seem to be as affected, which is part of what would make the prominences so interesting to look at.
Yeah. Although there you do see a difference, so it's possible, because a lot of time you can have a prominence eruption with not much of a flare, right?
Yeah.
But still, that's interesting.
Yeah, but we could still see a lot of flickering in 131, especially, around the
Yep.
foot points. I don't think anybody's ever thought to look at a prominence in 131 specifically.
Huh.
Yep.
Okay, if there is no more question, we can thank our speaker again for a very nice talk. Thank you.
Thanks.
Thank you.